we are considering the flow with no external forces and of course trying to find solutions to problems by using momentum equation and the system of the flow field. And therefore we continue that and we try to see through by solving another example that we have taken from the book of Sengel and the one that I have described to you, that we have taken as a textbook for this course. And therefore this example 6.3 can be seen in the book. I mean, that's why I have mentioned about the book. The force to hold a reversing elbow in place. Earlier, there was an exercise that we discussed where there was an elbow. The fluid is moving through a pipe, and you know that we use different kind of these things like T-points or T-junction, T-union, elbows, etc. if we want to move the direction of the flow, and we connect them to different pipes. So that's where these things are used. But at the same time, it is important for us to know that how much force a certain thing will need to support, to withstand the flow field. The pressure that will be there, the velocity that will be there, and the other things. Otherwise, if these things are not considered, then that utensil, that product that has been made can break down. So these are the things that we actually consider when producing something, when the products are made, when they are designed. The application of the fluid, when the knowledge of fluid mechanics is applied there, and we use this knowledge, we use the equation to determine the forces, how they will act, and how they will affect the motion, and what we need to do so that whatever product, whatever thing we are trying to make can withstand that and the flow can take place smoothly. That's the purpose. So here is another question. In this case, they say the reversing elbow, that is the elbow in the reverse direction as compared to what we discussed in our earlier example. The deflector elbow in example 6.2, that is the earlier example that I am also referring again and again, is replaced by a reversing elbow such that the fluid makes a 180-degree U-turn. That is, it is exactly opposite by 180 degrees before the fluid is discharged. And that has been shown, that can be seen in figure 6.21. The elevation difference between the centers of the inlet and the exit section is still 0.3 meters. Now determine the anchoring force that is needed to hold the elbow in place. So when the fluid is flowing, with the force that has been taken or indicated in this example, they want to know that it will not break down. It can withstand the pressure that will be generated for this given problem. Now we look at the solution. The inlet and outlet velocities and the pressure at the inlet of the elbow remains the same. They are the same as in the previous example, but the vertical component of the anchoring force at the connection of elbow to the pipe is 0 in this case. So therefore, the Z component of F of R is 0, and there is no force or momentum flux in that direction. The horizontal component of the anchoring force is determined from momentum equation written in x direction, noting that the outlet velocity is negative. Since it is negative in the x direction, we have now again what we are doing, trying to write down the equation, the momentum equation. And therefore, this will be f of Rx, that is the component of f of R in the x direction, plus the pressure at point 1 the gauge pressure at point 1 times the area of cross section of the pipe at that point, or of the elbow in this case at that point, and this equals beta 2, the flux correction factor that we defined in our earlier discussion, and that is required for considering when we are considering momentum flux. Then beta 2 into rate of change of momentum, that is m dot, that indicates the rate of change of m with respect to time, minus the velocity v2, or the velocity at point 2, minus the same quantities at point 1, and they can be written as this equation. So f of r of x turns out to be this quantity, and that follows from the above equation. Substituting their values, they turn out to be minus 2591 newtons. Therefore, the horizontal force on the flange is 2591 newton, acting in the negative x direction. So the elbow is trying to separate from the pipe. So this force is equivalent to the weight of about 260 kilogram. Remember, we are saying this is about. Note that it's not exact. Why? Again, as you know, we have from Newton's law, F is equal to m into a. And if this can be written as mg, acceleration is replaced by acceleration due to gravity, and here is the mass, and F is the force. So the force is determined to be 2591. G is, we know, 9.8. 981 centimeter per second square, but when we convert it into meters, then the units are changed, and then they are 9.8. So 9.8 is approximately being taken as equal to 10. So just as a rough estimate, if we divide this by 10, it will be 259, which is approximated to 260 kilogram mass, and thus the connectors must be strong enough to withstand this force. So these are the things that we need to consider, and this is the diagram in which the reverse elbow is shown, and you can see the pressure and the control volume that has been taken or that has been considered in calculating the equation for momentum flux, and from there the other values that we needed to know is shown here as the dotted line in the red. The force components are here in the x direction as well as in the z direction, shown through the green thick line. The fluid flow is being moved in this direction, entering here and moving out in the reverse direction, and we have tried to calculate then the force that is needed, which is equivalent to be about 260 kilogram.